Welcome to today's lesson. Actually, today we are going to look at static equilibrium, meaning that we are going to look at objects which are not moving. And in particular, we're going to look at a rudder, which is leaning against a wall, where there is an object actually placed on the rudder. And we want to see the forces which are there and then develop concepts so that we can apply them to any other problems that is asked on static equilibrium on the rudder. And therefore, I invite you to this important lesson, which I have called important. My name is Siamasaka Kilian Dennis. And so there we go. Okay, so as I indicated, I said we have a rudder here, which is leaning against the wall. This is the wall, and then this is the floor. So this rudder is actually arrow. This is the length of the rudder, and then meaning that its weight is concentrated in the middle, and therefore this is why I said mg. This is where the concentration of the weight of the rudder is. And then from the floor here down at x meters, the distance which is given as x, there is an object which is placed, which we have called the mg as well, but with the capital M. So we have placed an object there. So these are the two forces for the weights: the weight of the ladder and the weight of the object. The other forces which are actually at play is that if this ladder is not to slip, it means that there is a resisting force towards the wall, which is the friction. We have noted it with the F here, which is the friction. And we are aware that this rudder is not going down. It's not sinking, going down. It means that there is a force which is also pushing it up to remain in position where it is. And this is what is known as the normal force. We have quoted the normal force here. Similarly, where the rudder on top here on the wall where it is resting, it is not going inside the wall. It means that this wall is pushing against the rudder. And this is the force which is there, which is the normal force, which we have called the FW. So basically, this is the identification of the forces which we have actually outlined here. There is no friction. We assume that there is no friction between the rudder and the wall. Okay. And so I've already explained that the normal force, N, is the normal force on the floor. FW is the normal force on the wall. Fs is the static friction force between the rudder and the floor. And mg is the weight of the object on the rudder. And another mg with a small m is the weight of the rudder. Other things to consider is that actually they have already outlined them. I said there is a distance. This object is x distance from the floor. Okay, and then there is an angle theta between the rudder and the floor, which we have indicated here. Theta is the angle between the rudder and the floor. And so we need to, when we are dealing with a question on actually static equilibrium, and in particular, in our case now, we're looking at the rudder, it means that we need to resolve these forces into components. Why are we doing so? Is because we will be required actually to get the moments of each of these forces. And therefore, as you are aware, a moment is actually the force multiplied by the perpendicular distance from the point of action. And this is what we have done here. For the weight of the ladder, the force which is perpendicular from the point of action from down here, which is perpendicular to it, would be L over 2 cos theta, considering that the length of the ladder is L, and therefore in between it will be L over 2. That's why we have multiplied L over 2 cos theta. This is the distance which is perpendicular to the weight, which is this force of the ladder. We also need to identify the distance which is perpendicular to the weight of the object, which is mg here. The distance is this distance from here up to there, which is x. We said this distance is x, which is from the floor up to where the object is, it is x. And therefore, this distance here, which is adjacent to this angle, will be x cos theta, and is the one which is actually perpendicular to the weight of the object. The other one we can resolve into components is this force here, which is Fw, which is the force exerted by the wall on the ladder. This force also, especially considering that this angle here is alternate to this one here. It means that angle theta here is the same as angle theta. And then this side, which would be perpendicular to the force, would then be L sine theta. So this side, since it's opposite that angle, it will be L sine theta. This is very important because it's a basic concept that will help us to identify the forces and the distance. And the distance, which is perpendicular to the force, is very important, because if you miss this concept, it means that we cannot proceed with the actually solving the problem. So it's important that we pay particular attention to this important aspect. And as such, we will now proceed that we have known how to resolve the forces into components. Okay. And so for a static equilibrium system, we need to know that the basic concept which is there is that all the forces which are adding up in the x-axis should add up to 0. So this is what we have done here. We have said all the forces in the x-axis should add up to 0. And the only forces we can identify here which are in the x-axis are actually this force here, which we have considered to be negative Fw, and the frictional force, since it's in the positive x-axis, which we have considered to be positive. So these two here, when you add them, they should add up to 0. This is what we mean here. And so if the frictional force, which is static, should be actually, when added to another force, which is opposing it, should be equal to 0. And then if you equate this, it means that this one, the frictional force, would be equal to actually the force on the other side, which is exerted by the wall. So Fs is equal to Fm. What it means that we are saying, if this ladder is not moving, it means that this force, the frictional force, should be equal to this force here, which is also horizontal, Fw. Also, we have to resolve we have to add up all the forces in the y-axis. And so we note that here, the forces which are pointing downwards is mg for the weight of the ladder and mg for the weight of the object. And then the one pointing up, which we have stated to be positive here, is the normal force, which is the force exerted by the flow on the ladder. And therefore, as I indicated, we are saying the downward force is this one, mg, which is the weight of the ladder, and the other one, which is going down, mg, which is the weight of the object, and the other force, which is going up, which is opposite to this one, which is vertical, is n, which is the normal force, which is exerted by the flow on the ladder. And these two, when you add all these three forces here, they should add up to 0. This is what we are saying here. Very simple indeed. So you can say actually mg, which is the weight of the ladder, plus mg, which is the weight of the object, should be equal to the normal force, which is actually pointing upwards. These two are pointing downwards. We are also required to actually balance up the torques. And as you may be aware, a torque is merely the force multiplied by the perpendicular distance, which is from the point of action, which is actually a moment. And therefore, we need to add these torques for all those moments which are actually in the clockwise direction, as well as those which are in the anti-clockwise direction. So our torque here for the object, it would be mg, which is a force for that object, multiplied by the perpendicular distance to it, which is x cos theta. Remember, this is what we said here. So it would be this force here, mg, multiplied by the distance which is perpendicular to it, which is x cos theta. And then plus mg, which is actually the weight of the ladder, multiplied by L over 2 cos theta, which is actually the distance perpendicular to this weight. So what it means is that we are saying this is the weight of the ladder. The ladder has a distance of L, and therefore a distance from the middle, if it's uniform, it is L over 2. This is the distance, the half the distance of the ladder. And then you multiply it with the distance which is perpendicular, which is L over 2 cos theta. This is the one which is actually perpendicular to that force. And so then we have minus Fw multiplied by L sine theta. This is negative because it is in the anti-clockwise direction. So we have this force here, Fw, and you have to multiply it with the L sine theta, which is perpendicular to it. And these forces, these moments, when you add them, they should be equal to 0. And this is what we mean here on the torque. So if we are to use now the principle of clockwise moments, which should be equal to the sum of actually anti-clockwise moments. So what we mean here, this same, we just identify those which were clockwise, and we said these are clockwise, and this one Fw is anti-clockwise. Fw multiplied by L sine theta is actually anti-clockwise. And so this equation, we can make Fw, which is the force, this force here on the wall, we can make it the subject of the formula. And when we make that one the subject of the formula, what will happen actually here is that you bring this one, which will be divided by everything here, then you are going to remain with the Fw on the other side. This is what we have done. This is now mathematics, simple mathematics of rearranging actual terms. And so this can be further broken down. What we have done is that since L sine theta is dividing with this part and this part here, it means that you can separate it. Just get this part here divided by that one, which is mg multiplied by x cos theta divided by L sine theta, as well as mg multiplied by L over 2 cos theta, which is this part here, divided by L sine theta. We have merely separated them. And as you are aware from trigonometric identities, cos theta over sine theta is cot theta. And this is what you wanted to achieve here. So we are saying actually now where there is cos theta over sine theta, we can substitute the cot theta. Similarly here, when you divide this divided by this one, the error will cancel out, and therefore we are going to remain with the mg over 2 cot theta. And then you can factor out the cot theta since it's common here and here, and this is what you get. And you remember, we said that the horizontal forces, the frictional force was equal to Fw, and therefore this equation which you have found here, we can equate it to the static friction, meaning that they are the same. So this one gives us actually this same equation. And therefore, we would want to see the effect of actually moving this object up. What would happen to the friction in the first scenario? And the second scenario, we want to find out if the angle increases by moving the rudder near the wall. If it increases, what happens to the friction? And so I have a simple question here that we are going to go through in order to analyze that situation. The question reads as follows. A rudder with a mass of 4 kg and 5 meters long is leaning on the wall. An object with a mass of 50 kg is placed on the rudder at 1.5 meters from the floor. Assume that there is no friction between the rudder and the wall. The first part of the question is we need to calculate the friction force between the rudder and the floor if the angle between the floor and the rudder is 30 degrees. So we merely actually use this same equation which we have actually formulated here. And so all we need to do is substitute the quantity that we have been given. We have been given that actually the object has a mass of 50 kg, which should be multiplied by 9.8 for our acceleration due to gravity. Again, multiplied by, and then divided by 5, which is the length of the ladder. And then this should be added to m g over 2, where m is the mass of the ladder, and the g is acceleration due to gravity, which is 9.8. Then all this divided by 2. And then cot 30. We are told that the angle between the rudder and the floor is actually 30 degrees. And therefore, when you simplify this, it gives you 288.2 newtons. So the first part, we are saying this object was placed at 1.5 and it gave us 288.2 newtons. Now, let's see if this object is moved up and these other parameters remain the same. We just move the object up. So we move this object from x, which was 1.5, move it now to 2 meters according to the equation, second part of the equation. So where they are saying calculate the frictional force when the object is moved to 2 meters from the floor. So we merely use this same equation, but now we substitute 2 there. And what we notice that the friction has increased to 372.9 newtons from the previous one, which was 288.2 newtons. So what this one shows is that if the object moves up the ladder, or if you are climbing a ladder, as long as you are going up the ladder, it means that you require a higher friction force. And what that entails is that you are likely to actually to slide with the ladder. So the ladder is likely to slide when you go up. As you are climbing up, the likelihood for the ladder to flip actually increases. The second part of the question is actually the same question which we discussed earlier, but now what has changed is the angle. The angle between the ladder and the floor has increased from 30 degrees to 40 degrees. In other words, we want to find out what happens to the friction when this ladder comes closer to the wall. And by this ladder coming closer to the wall, it means that the angle is increasing. So what will happen to the friction force here? And so what we do is that we actually merely use this same equation, and we assume that it was at the object was at 1.5 meters from the floor, and these other parameters remain the same, but we have moved the ladder closer to the wall and thereby increasing the angle to 40. And if we calculate the friction here, it becomes 198.4 newtons, which is lower than when we had actually used the angle 30 degrees. These are the parameters which are the same here, but we only increased this one. So previously, when we had 30 degrees here, we found 288.2 newtons. While after increasing the angle to 40 degrees or pushing the ladder closer to the wall, the friction actually reduced. So there's more stability as the ladder goes closer to the wall. In other words, the likelihood of slipping with the ladder reduces as you go closer to the wall. So these are a basic concept that I decided us to look at today. And I know we'll look at these application of these concepts to many other problems that will enable us to understand the concepts for objects in static equilibrium. And so I hope you have enjoyed this lesson, and I hope you will dearly subscribe to my YouTube so that you continue getting these interesting lessons. I thank you.